We come back together. I've got some very interesting news. We have 38 people now joining us through the webcast online. So that's gone up from about 30 earlier. So in addition to those of us here in the auditorium, there's 38 people joining us through the webcast.
And it will be archived. They can see more.
Yes, that's right. We're archiving. This is a free service at the University of Missouri. All speakers have agreed to allow this because we don't want to archive or webcast someone against their knowledge or will. But the situation is that we just provide this as a service through the seminar series. And really appreciate Sue and the others' help in getting this all together today. Oh, very good. Our next speaker is Professor Mark Prelas from here at the University of Missouri. And he's with the Nuclear Science and Engineering Institute. And again, you can find the vitas of the people or the bios of the people speaking on our website. Either the best place I think to go would be research.missouri.edu. So, Mark.
Well, I'd like to thank Rob for inviting me to give this presentation. I published in this area pretty early on. I think my last publication was about 1993. And what I'm finding is that very little has changed. We all are kind of blindfolded and trying to work the puzzle. But thankfully, I have some colleagues that I have kept up with, George Miley and Tom Dolan. Imagine all of you know George pretty well. Tom worked for IAEA, and he was manager of the physics division. He's done quite a bit of review on low-energy nuclear reactions. And so what I want to talk about is kind of some of the work that kind of throws a monkey wrench into this whole concept. How does the transmutation occur? And then there are some observations from my earlier work that I want to talk about. The outline, George was kind enough to provide some of his slides on transmutations, as Tom was as well. Then I want to revisit some palladium loading experiments that were done here at the university in 1989 using a magnetic mirror as a plasma source. And then I want to discuss something that is not directly tied to this, but it does have an indirect tie. And it's based on some work we're doing here with regard to loading materials with hydrogen. But one of the interesting things from these observations is that we can maybe support some of George's theories. The transmutation description is that there are essentially observations that we have seen reported in prior work where you've actually seen the materials being generated that were not present in the initial palladium electrode. And basically, these types of events, the transmutation events, have been seen in a variety of experiments. George, I recall, sent me his initial work when he did the transmutation work, wanted me to review it to see what I thought about it. And that's where my history began. I actually looked at that particular data and gave him an opinion. Since that time, many other observations have occurred in Japan, Russia, Italy, US. So many groups have seen similar results. The Miley experiment was basically done with a classical electrochemical cell. The electrode may have been a little bit unique in the sense that what he did with the palladium was did a platinum palladium nickel thin film cathode, which was sputtered on different dielectric substrates. The cathode basically was structured with the thin film coating and then the anode. And the substrate, he used various types, glass, quartz, etc. The results that he saw were that basically he was seeing peaks of different elements at 20 to 30, 50 to 80, 110 to 130, and 190 to 210. Now, none of the particular species he saw were unusual in the sense that they naturally occurred, but what was unusual is that if you look at the natural abundance of the element, these were way out of kilter from the natural abundance. The production rate, which he postulated in terms of atoms per cubic centimeter per second versus A, shows zones of high yields in the peak areas of about 10 to the 16th atoms per cubic centimeter per second, with low yield zones. He basically looked at the isotope abundance using SIMS, broad scans of the surface, and was able to show that there were localized areas of reactions. In addition, again, this is pretty similar to what has been presented before, but there's evidence for nuclear reactions that he had looked at basically using CR39, and the particles that he saw, he had MeV charged particles and evidence for soft X-rays. Other groups that I thought might be worth reviewing, because I think some of this work pretty much, again, supports these observations. There's transmutation by diffusion of deuterium gas through thin films by Iwamura. In essence, this was a very simple experiment where deuterium gas was pressurized on one side of a structure made of a palladium complex, and transmutations were observed in the cesium and strontium. The experimental system is shown here, and again, it had a number of very interesting diagnostics associated with it. The structure of the film was basically a bulk palladium material of about 0.1 millimeter thick and about 1 inch by 1 inch. There was a calcium oxide layer, and then thin film of palladium, and then a surface film of cesium, and a separate experiment with the surface film of strontium. The observation was that as basically time went on during the experiment, the cesium level decreased and a promethium atom or element increased with time. And if you look at the other experiment with strontium, it was molybdenum being the element that was created and strontium levels decreasing. Now, if you look at just natural molybdenum, and this again goes back to what I had earlier mentioned in George's experiments, that there was nothing unusual about the fact that he saw some of these elements. It was the abundance that was unusual. If you look at SIMS of natural molybdenum, what you see is a SIM showing abundance at 92, 94, 96, 98, and 100. But in this particular experiment with the D2 flow, it was the 96 mass number that began to stand out. Now, Iwamura, of course, had postulations for possible reactions for this, namely cesium, deuterium, going to promethium and then the strontium plus 4 deuterium going to molybdenum. Like you, that would be a very puzzling reaction, so I would feel that the evidence for that reaction certainly is questionable, or not the evidence, but the reaction itself. There must be some other mechanism. Another group, Mizuno from Hokkaido University, also did a very interesting experiment with regard to transmutation. If you look at the material before and after, before there was evidence of palladium and platinum, but afterwards abundance of elements began to show up in an X-ray spectroscopy study. A third one is Adamenko, which basically just used a cathode beam anode type approach, bombarding a target with E-beams. In this particular experiment, there was evidence of an explosive type energy, and basically the explosive energy was greater than input energy. And when X-ray electron probe microanalysis was done, there was evidence of materials being created other than what was originally in the electrode. This is more or less a summary of the elements. If you look at the periodic table, basically in Miley's experiments, it was calcium, titanium, chromium, manganese, iron, cobalt, copper, zinc, etc. There was some overlap with earlier experiments. And other experiments showed magnesium, silicon as potential differences in materials that were created. Now, one of the studies that I did early on, this was about 1989, we used a magnetic mirror device called the Missouri Magnetic Mirror experiment. And the idea there was basically using a plasma source to load the palladium. We performed 3 experiments from about, I think it was about 3 days after the Pons-Fleischmann announcement to late May. And there were some very interesting results in this particular set of experiments. The mirror is basically set up as it could be used as a cusp or a single or a mirror device. It had a radius at the point of about 0.15 meters and at the cusp at about 0.42 meters. The width was about 0.13 meters. Maximum radial field was about 0.4 Tesla. Maximum Z field was about 0.68 Tesla. It utilized microwave heating primarily with electron cyclotron resonance heating with a 2.5 kilowatt source. None of the other heating methods were used in this particular experiment. It was just based on ECRH at 2.5 gigahertz. Plasma density was about 10 to the 18th atoms per cubic meter. A hot electron ring was formed, but that mostly resided in a very small cylindrical plasma around the annulus of the mirror, and basically the bulk electron temperature was actually fairly low, about 1 to 5 eV. The hot ion temperature was about 15 keV, but the bulk ion temperature was about 0.5 to 10 eV. Plasma volume was about 9 liters. In this particular experiment, we utilized BF3 neutron detector, a sodium iodide detector. It was about a 3-inch sodium iodide with an MCA for gamma spectroscopy, thermocouples, and a residual gas analyzer. The palladium samples were put into two structures. One was a classical an ion analyzer, or ion energy analyzer. In essence, it had an aluminum case, and then basically it had a grid that allowed the ions through, and a target, which was the palladium target. We were able to adjust the voltage on the grid to adjust ions being able to reach the palladium target. The second experiment was basically one that just utilized a traditional Langmuir probe, which was a palladium target just mounted on the tip of a probe. Now, the first experiments that we ran used the ion energy analyzer. We had a base pressure of about 9 × 10⁻⁷ torr, and we filled this chamber up with, well, I didn't have the number here, but it was about on the order of 10⁻⁴ torr of deuterium, and then created our plasma. We did neutron background rates, and the neutron background was about 1.1 ±1 neutron every 7-minute count rate using an argon plasma. And then basically when we utilized deuterium gas, that count rate, background count rate was 3 ±1.73 every 7-minute counting period. We then turned on the plasma, and what we'd noticed was that basically both the neutron counter and the gamma counter went up exactly the same in time. We had a computerized system where we were able to do analysis of the data. The data went straight to the computer, so we had a real-time view of count rates of both gammas and neutrons. And the experiment was done where we cycled it with plasma, no plasma, plasma, no plasma. And what we saw was that count rates went up with the plasma, and they went down, but not in it didn't go coincidentally with the shutoff of the plasma. It decayed. And then basically, when we turned the plasma on, we had the same sort of behavior. Count rates went up above background, then went down when the plasma was turned on, off. And we cycled it several times. And one of the more interesting things is that when we saw the largest burst of neutrons and gammas at the end of the second cycle, they were coincident with a decrease in temperature going from 110 Fahrenheit to 80 Fahrenheit. Now, the second experiment, which took place in April, this one also used an ion energy analyzer. And in this particular setup, again, we had a base pressure of about 10 × 10⁻⁷. We increased our count rate, did 30 minutes. We did both argon and deuterium plasmas. The plasma action with argon actually helped clean the surface of the palladium. Palladium was placed in the D2 gas at a pressure of about 10⁻⁵ torr, turned the plasma on, and then basically we got a peak neutron count rate of about 297 ±17.2 counts over a 30-minute counting period. After about 9 hours, the palladium sample temperature rose, and then basically neutron count rates abruptly dropped above 100 degrees Fahrenheit. The third experiment was done with a mounted Langmuir probe, and we did both plasmas and just variation of gas pressures in this particular setup. We basically did very long counts here. We had a peak neutron production rate that was about 100 times sigma of background. But what was interesting with this experiment is that about 200 hours into the experiment, that would be this particular burst here of neutrons, we had our sodium iodide detector set up to look at gamma spectra. And this is a spectra that we saw coming off. We had a broad peak, which is not unusual for sodium iodide. Sodium iodide is not a terribly efficient spectrometer material, and it's known for broadening peaks, so that's not unusual. It had its Compton edge. This particular peak was due to the fact that the sodium iodide detector was inside of a very thick lead pig that was open up to the or actually aimed at the sample. So this is essentially a Compton scatter high gamma, which probably results from the same event. I mean, this looks like a very classical experiment where you have a leaded shield around a sodium iodide detector. So basically, that particular event, that release of 8.1 MeV gammas at 200 hours, was somewhat unusual. And we have talked with George Miley and Heinz Hoare about it, and they have scratched their heads, and they think basically that they have a theory for it, which involves clustering. And that may or may not pan out, but in this business, that's pretty standard. You have a theory, you hope it tests data correctly, and then if it does and it meets all the other observations, then you can formulate new tests of the theory. But one of the things I would like to also talk about, and this is somewhat not related to the loading of deuterium, but I think this is interesting in the fact that we have some indirect evidence that you can cluster in materials other than palladium. In our case, we've been working at the university with diamond for quite a while. We have been doing diamond loading or hydrogen loading experiments in diamonds since the early 90s. And the idea of doing that was, it started out as a means of understanding the semiconductor properties of CVD diamond, which had a very large hydrogen concentration in it. But we found that diamond in the CVD phase was able to store quite a bit of hydrogen. And so we began looking at what those limitations were for diamond. We use a technique called field-enhanced diffusion with optical activation. It has many similarities to electrochemistry in the sense that if you look at a typical experiment, we do this in the solid state, we have essentially diamond samples which have electrodes top and bottom. In the middle, we put an impurity that we wish to load into the diamond. So we make a sandwich of diamond, impurity, diamond, with two electrodes. The sample is heated to temperatures of about, well, we can go up to about 1100 degrees centigrade. And basically, we can put an electric field across the sample. And we also utilize a laser. And the reason for the laser is that the ion inside of the diamond sample, once it's in solution with the solid essentially is perpetually in an ionic state with the presence of the laser. Otherwise, it recombines, so the laser extends the lifetime of that ion considerably. The technique has been used to dope our diamond samples with various materials. We basically developed it to try to make N-type diamond, but we use this technique specifically to look at hydrogen loading. In our hydrogen loading experiments, we used the following diagnostics: prompt gamma analysis via neutron activation, which is a means for looking at the bulk hydrogen density. I'm almost done. Secondary ion mass spectroscopy and mass change measurements. We tried various samples. We had a series of CVD samples. More interesting one was a sample that came out of Daimler Benz. But we had samples from Kobe Steel, Aztec Corporation, and Norton Diamond Film. And then plates, diamond plates. So if you look at our list of samples, this is what we had. And basically, here are the preliminaries. If you load a diamond lattice with hydrogen to get a 1-to-1 ratio of hydrogen to carbon, the mass differential would be about 8.33%. So basically, if running our first test using FEDOA to load the hydrogen, we ran a sample for 48 to 51 hours. If you look at Kobe samples, these are CB, and Ulm is the Daimler-Benz sample. We had hydrogen loadings of about 2.2%, but a very interesting result here of 21.22 with the Ulm sample. The Ulm sample was such that we can only really do PGA on it. It was a very fragile sample, and so we were limited to this sole method of doing the bulk analysis. If you did diamond plates, again, you got numbers very similar to CVD, like the Kobe Steel sample, of about 2%. If we loaded at a shorter time period, of course, numbers went down a little bit, but the Ulm sample still remained above 17%, meaning that in that particular sample, we were getting better than one-to-one loading. So consequently, we think that we have some other results which I'm not at liberty to talk about, but that we are seeing some clustering of hydrogen in these lattice sites in the diamond. So I think George's theory may have some legs, and I'm hoping that he develops that and is able to come up with a very comprehensive explanation of this 8 MeV gamma. Thank you.
But has anybody studied the effect of hydrogen absorption on the hardness of diamonds?
Yeah, we actually, yes, we've actually done some work with that, and it actually increases the hardness a little bit, about 10 to 20%, depending on the loading.
And you've never done it with deuterium, have you?
No, but that would be interesting. That might be a next step.
Just curious if you've ever gotten a Shockley barrier between a P-type and an N-type diamond.
Oh yeah, making a Schottky barrier is pretty easy on diamond. Yeah, that was some of the first work we did in the late 80s, early 90s. But again, you know, the open circuit voltage on a Schottky is about 0.7 volts. But we did make a diamond with about 2.6 volt open circuit.